All right. Good morning, everyone. I'm Brendon Nicolas. My teammates are Kevin Giardinieri, Joshua Gelber, and Dev Patel. We are Renewable Cube. Thank you very much for attending our presentation. We hope you enjoy it. We all know that there are many people around the world that have difficulty getting clean water. That is something we constantly get reminded of, but we are rarely given the numbers behind it. Well, 2.2 billion people worldwide struggle attaining safely managed water. Furthermore, only 54% of Africans live in areas served by a piped water system. Most people affected by water scarcity are from third world countries where there is a high premium for access to clean water. This is a real problem because we all know how vital clean water access is to everyday life. In order to tackle this problem, our team set out to create a self-sustaining water filtration system. We designed this system to be low cost and scalable in order to maximize its effectiveness and outreach. With these ideas in mind, we hope to bridge the clean water access gap because clean water sets the tone for a healthy life. You might be thinking that there are already many filtration systems out there. UV filtration systems are typically designed for whole house use and as such require a piped water system. The portable filtration systems out there aim for practicality and only have sediment and carbon filters, which do not remove the microorganisms already in the water. Our system is meant to be the best of both worlds.
So Renewable Cube brings to the market a water filtration system that's powered by a renewable resource system, and it's capable of removing sediment, organic compounds, and bacteria and viruses. The water is pushed by gravity through the sediment and carbon filters, and once it's in the reservoir, a spigot is used to pull the water through the UV filter. So unlike our competitors, our system can filter out viruses and bacteria because we implemented a low-cost UV filtration system. Our system also is self-sufficient and does not need access to an electrical grid. So during our research, we found that in certain countries in Africa, residents like to use clay vessel pots or flower pots in order to clean their water. So they like using this method because it's relatively cheap and easy to make at home. The one downside to this is that if you're making it at home, you can potentially make it poorly, and in the future, it can crack. And so through those cracks, harmful pathogens can seep through down and land inside of the drinkable water. So Renewable Cube, in order to deal with these issues, we use a carbon filter and a ceramic filter. So our carbon filter uses a process called chemical adsorption. So here, the compounds inside of the contaminated water react with the activated carbon, and they get trapped on the surface of the carbon filter. So when the carbon activates, basically it's increasing its surface area exponentially. And by doing this, it gives it the ability to trap and isolate those harmful pathogens on the filter. For the ceramic filter, you can imagine that inside of this filter, there is an intricate and very complicated maze, and it makes it very difficult for the harmful pathogens to get out of that ceramic filter. We also found another popular method to cleaning your water was using chemicals, but we found that if you really aren't trained well, that you could potentially add more chemicals than are needed for the water, and you can make it hazardous to the people who are drinking it. So in our system, we use a UV light filtration system where anything that the ceramic or carbon filter failed to deal with, the UV filter will essentially take care of. So the UV rays hit these harmful pathogens and essentially destroy their DNA, and it gets rid of their ability of these harmful pathogens to replicate and reproduce.
For our scientific model, we were able to create a function in Python that returns the amount of power needed to power the UV light, the length of sun exposure the solar panel needs, and the total time it will take to filter the desired amount of water. This helps to maximize the UV filter life and reduce the load on the battery. In terms of our technological component, we were able to configure the UV filter with a battery that is charged by a solar panel. In addition, we were able to configure an Arduino along with a script that returns the current level of water in the system. We will now demonstrate our project.
Hello everyone, we're here at the Raritan River and we're about to fill up this top bucket with the rest of our water. The water will then go through a sediment filter and then through an active carbon filter after that. And we'll just have to wait and see and let the filters do their magic. This is our solar panel, and as you can see from the blue light here, that is right now collecting energy from the sun. Then it's transferring this energy into our battery, which is stored inside this box here. And then here you can see, based on the green light being on, that it is collectively transferring the power from the battery into the UV light. And then once we hit the spigot, the water will go from inside through the UV light and come out here into this jar. Since we know everything's working correctly and our bucket's empty with water, let's get some clean water. I'm thirsty, I don't know about you guys.
So for validation and testing, we did water tests to measure the difference from water quality from pre and post filtering. These tests tested the water on hardness, chlorine, alkalinity, pH, nitrate, nitrite, copper, and iron. In the table, you can see that unsafe metrics are in red. In the filtered water, every metric is safe. And in the unfiltered river water, we can see in 5 areas the metrics are unsafe. And the graph on the right shows the time it takes to filter various amounts of water. Through testing, we were able to find that the sediment and carbon filters filter at a rate of 2/3 gallons per hour, while the UV light filters at a rate of 15 gallons per hour. So for project management, for sharing responsibilities, we met virtually multiple times a week. And we also met once in person each week to build the project. And we also got COVID tests bi-weekly to make sure we weren't giving COVID to each other so we could work safely. And then for the challenges, when we first initially chose this idea, we were expecting to have full access to Rutgers labs and all the tools available to us, but unfortunately we did not have that. So we were only able to use home tools. And then also for the Arduino, we were not able to attach it remotely, and therefore we're not able to use it when it was not connected to a computer, which made it a little more difficult. So why choose us? There are 2.2 billion people across the world who lack access to clean drinking water. Systems that currently exist often rely on access to piped water systems or do not clean the water well enough. Renewable Cube offers a system that is self-sustaining and able to eliminate 99.9% of contaminants at a fraction of the cost. Invest today and let's all have clean water for a clean life. Produce it yourself when there is no one else. I'd like to give a special thanks to Dr. Jafar and Yufei for helping us throughout this project.
As you guys were sort of putting this together, did you give any thought to reliability of individual components in the system, especially given the fact that, you know, the Renewable Cube might be used in places that there aren't a lot of Lowe's stores and you know, places to actually get replacement and whatnot. So I'm curious, can you give me some thoughts, your thoughts about reliability and you know, design and upkeep of the system?
Yeah, so in the appendix, we have a chart. Could you go to that? One more. Could you keep going? Yeah, here. So we had a risk assessment in the appendix where we kind of see each individual part and if there's an error, how detrimental it is to the system. You know, if the filters break, it won't work properly. And unfortunately, due to budget constraints, we didn't have the ability to, you know, to buy new filters if they broke. So that would be a big issue. Now for parts such as the Arduino, it's nice to have, but it's not necessary. So if it doesn't, if it's not attached, it doesn't really make a difference. So in this assessment, we kind of broke down which parts and what will happen if there's an error or malfunction.
Great, thanks. Nice
How
work.
how scalable is your system so that, let's say that a village in Africa that's got 100 people or so, to provide the water that's necessary for them, how quickly can they turn that around to provide, proper water?
Yeah, so this system is more designed for individual families as opposed to large villages. So it's supposed to be able to provide the daily needs for individual families. So they can, if they have a river next to them, they can gather water and dump it to the system, and a few hours each day get enough water for the day if they run it through the system.
But even a family, and probably in Africa, there may be a fairly large family, how quickly, and what could you provide to, let's say, a family of 6 or 8 or 10, how quickly they have to wait?
We had a chart that says like how many gallons, and assuming that like a person needs a gallon of water a day. Josh, can you go up to the chart that says how long it would take to filter an X amount of gallons?
Yeah, Kev, can you scroll up?
Oh, right, down.
Yeah, you missed, yeah.
So like for a family of 6, around 6 gallons would take approximately close to like 9 hours. So if they ran the system overnight, by the time they wake up the next day, they would have enough water for the 6 people.
Gotcha. So they would have to do it in advance.
Yeah.
Okay.
Yeah, you might want to send that over to Flint, Michigan. They're having some water problems.
Yeah.
So one question though for you fellas, if you did the cost calculation, what's the cost of ownership for the Cube system versus just buying, Kirkland branded bottled water?
Right. So the total system approximately costs close to 300. It's in the appendix. It has a cost breakdown. And this system will give you enough water for like a long period of time, opposed to just continuously buying Kirkland water bottles, which will, if you buy like a 40 pack, assuming it's like $5, it would run you quite a number throughout the year.
Got it. Thanks.
What do you have to do to maintain the system? So you're filtering stuff, you're obviously going to have to do some cleaning, of the system because you're collecting whatevers and you've got to get that out of there. So what kind of maintenance is there involved to keeping the system functional and clean?
Right. So to keep optimal function, there's a scrubber that's included, and the main maintenance that you'd have to do is scrubbing those ceramic domes and carbon domes to make sure that the pores aren't completely clogged.
You'd also want to keep track of like the filter life. So we made a chart for expected lifetimes for each filters to keep track of when you should be making replacements. So you can see that the UV lights are pretty low maintenance, and so you'd only have to replace it about once a year.